Hello, I'm Param Rathore. Today we will learn about Braess paradox, how creating new roads could actually slow up traffic. This is part of my game theory SOS. So let's get started. So what is Braess paradox? This is an example of veridical paradox. It means that a paradox that is not actually a paradox. It is proved, it is true, it just seems counterintuitive. So the paradox is usually associated with transportation networks and brings out the fact which shows that adding capacity to a network can sometimes actually slow down the traffic. So first of all, we should be able to model our transportation network. The figure 1 shows an example of transportation network. So we are modeling it as a directed graph. We consider the edges to be highways and the nodes to be the exits where you can get on or off a particular highway. So here AC, CB, BD and AD are the highways and A, B, C, D are the nodes. So the goal of this figure is to go from A to B, and C and D are the two stops we can take in between. So one more thing here is, in modeling we are using the value at edge to denote the travel time that depends on the amount of traffic that edge contains. So for example, AD is written at 45. That means no matter how many cars are going through this route, the time taken by each car to go from A to D will be 45 minutes. Similarly, from D to B, the time taken is x by 100. That means if there are 200 cars going from D to B, then the time taken will be 200 by 100, that is 2 minutes for each car. So before going forward, let's denote formally what a game is. So a very common representation is using strategic form games. This is also called as normal form games. So it is a tuple of n strategies and the payoff functions. These are the strategies denoted by SI, and UI are the utilities or the payoff functions. Now here n is the set of players. There can be n players in a game, and for each player we have strategies, and for each player we have utilities. So a utility will be defined for every combination of strategies that can occur. So now how will we represent the figure, the game that we discussed before, into a strategic form game? So suppose there are 4000 cars, then n will be 1 2 to 4000. What will be s? S will be, so for all players, that is s1 2, so all players the strategies are the same, C and D. So what does C and D means? C means if we go through the route AC and then CB. D means if you go to D first and then B from D. So now NC are the cars that travel along this C route, and ND are the cars that travel along D route. Now the sum of these will be equal to N, and the utility functions are the reverse of the times, because utilities are usually payoffs and time is lost. So we are multiplying by minus 1. So the utility for a strategy is given by minus 45 minus NC by 100 if SI is equal to C. This means if the route is from here, then the utility will be 45 minutes lost here, and whatever is the number of cars going through this route, that will be NC by 100. that will be total time taken, reverse of that. Similarly, if we are going to D route, then the utility will be this. Now, to analyze these games, we define the notion of Nash equilibrium. So there are different kinds of Nash equilibrium. We will see pure strategy Nash equilibrium, which means that a player uses a single strategy. A mixed strategy Nash equilibrium will be when a player can mix a strategy, and each strategy will be defined by a probability distribution. So say here, if C is used 50% times and D is used 50% of the time by a single player, then it is a mixed strategy. But here we are not considering that, we are only considering a pure strategy. That means a player can only apply C or D. So the Nash equilibrium states that S1, S2 and Sn is a pure strategy Nash equilibrium if the cost, so if the players cannot benefit from going away from the strategies. So if say a strategy S1 star, S2 star, Sn star is a pure strategy only if a player suppose chooses some other strategy, and S minus I means all the strategies that are not that of that same player. So if a player chooses a strategy that is not this pure strategy, then they can't get higher payoff. So the payoff will be high maximum for this. So this kind of is also called as best response, because if suppose we are considering the player S1, then an S2 star, Sn star is denoted by S minus 1 star. Then what will be the strategy for the player 1? So for in a Nash equilibrium, that strategy has to be the strategy that will generate the maximum or the best response. So another way to denote this is using the best response correspondence. So given a strategic form game, the best response correspondence for a player is calculated using the same relation given here, and then all the Nash equilibrium will be when the strategy belongs to that best response. So the formal definition is okay, but how can we interpret this Nash equilibrium? And here is the interesting part. So one way is like a prescription. That means there is an advisor or a consultant that is advising all the N players how should you logically play this game. If the advisor recommends strategies that do not constitute a Nash equilibrium, then at least one player would find that they are better off by doing differently than advice. If the advisor prescribes strategies that do constitute a Nash equilibrium, then the players are happy because playing the prescribed strategy is the best they cannot do. They cannot become better off by staying away from it. Thus, a logical, rational advisor would recommend a Nash equilibrium to the players. Another way to see it is a prediction. So if all the players are rational and intelligent, and they all know that the others are rational, intelligent, and this kind of notion, then a Nash equilibrium provides one possible scientific prediction for the game: a self-enforcing agreement. So this can be viewed as an implicit or explicit agreement between the player, because once this agreement is reached, then there need not be any external means of enforcement, because if it is in the self-interest of the player to follow the agreement. If they don't follow, they cannot become better off anyway. And the last is evolution and steady state. So this is a potential convergence point of this process. So if the game is played multiple times, what will happen in the end? So this is like a long standing social convention that people are happy to maintain forever. This also explains biological evolution. There are many more interpretations, and you are encouraged to look it up. Okay, so let's get back to this. So, so what is the equilibrium traffic here? So if we consider the case when NC is not equal to ND, remember NC was this path and ND was this below path, then the routes will have unequal travel times because because this utility expressions, if they are unequal, then the times are unequal, and any driver on the slower route would have an incentive to switch to the faster one. So the players can become better off, and hence it's not a Nash equilibrium. So the only equilibrium, and if it is equal, if NC is equal to 2000 and ND is 2000, then it is a Nash equilibrium. And in this situation, what is the time delay? It will be 45 plus 2000 people go here and 2000 go here, so that will be 2000 by 100, 20, 45 plus 20, 65. 65 is a number you have to remember. Now we add a route from C to D. Our intuition says that this route should speed up the transport. So let's see what happens. Now just for easiness and simpler analysis, we are using the time as 0, so we can instantly go from C to D. Even when this is not 0, it's still possible realistically that Braess paradox or this kind of situation that we will encounter later is happening. Now, okay, so let's switch it again. So if n is n 4000, then again to represent this game, I'm using the 4000 players, and the strategy for each player will be either go C, that means the above route, D means the below route, and CD means go to C first, then to D, and then to B. Now assuming, and these are the numbers of how many cars are going to the corresponding route, and the utility functions are also very similar to calculate here. This so for example, I will calculate for the D1. So first, the number of cars going here will be ND, and the time taken is anyway 45 for any number of cars, and then here the number of cars will be ND, and the cars from this route, that is NCD, would also be in this edge. So the total cars will be ND plus NCD, and the time will be ND plus NCD by 100. So that's how the utility is calculated. Similarly, we can see for the others. So now the surprising result is that there is a unique Nash equilibrium. So and if there is a unique, so every person will use the same strategy, and that strategy is CD. That means go to C, then from C to D, and then from D to B. So there is only one Nash equilibrium, that is using the strategy CD by all the players. So why is this an equilibrium? This is an equilibrium because no driver can benefit by changing their route. Because if you calculate, all the other routes will come out to be 85 minutes, and this route, the CD route, will take 80 minutes. This is again very easy to calculate, and so you can check that the best route for any driver will be CD. So this gives you and because if every player uses CD, they won't be better off if they switch later. So that's one way to look at if it's a Nash. But why is it unique? So we haven't discussed much on this thing. So it is actually unique because this adding edge has made it a dominant strategy. Now what is a dominant strategy? A dominant strategy is a strategy. So there are three types of dominance: strongly dominance, weakly dominance, very weakly dominance. And essentially, what this says is, this kind of strategy says is, no matter how other people play, uh, one player, if they have a dominant strategy, if they play that strategy, then that will be their best response. So if you see the definition of Nash equilibrium, it is for a specific strategy. So the strategies for all the other players are known, and then the strategy for a player has to be the best one among the best one from the players. But a dominant strategy is a strategy that applies irrespective of whether people play and the strategy play any strategy. Okay, so that's the reason it becomes unique. But now see, if you calculate the time delay, it will come out as 80 minutes. And if you remember from 65 minutes that we calculated before, then even after adding a new road, we are at loss. So that's how it seems that adding a road actually slows down the traffic. Okay, so that's the end of this discussion, but I want to tell how you can move forward from this. So what are the big questions that you can take away from this small video? So first question is, does an equilibrium traffic pattern always exist? And the answer is yes. And then how bad Braess paradox can be for networks in general? So all these questions are very nice thinking exercise that you can do, and maybe look out more game theory and stuff to find out the answers. So it turns out that if the travel time function, for example here, for any edge is a linear function of the uh, number of cars going through that edge, then this Braess paradox is as bad as it can happen. So this uh, so there cannot be even worse stuff. That's only for linear, and this result was proven by Roughgard and Tardos in the paper How Bad is Selfish Routing. You should definitely check this paper out. And there are many more questions you can think of. How much larger can the equilibrium travel time be after the addition of an edge related to what it was before? So, and how to design networks that prevent bad equilibria from arising. And these are great topics that you can tinker and think upon. Some of these topics go into the depth of potential energy. So we calculate potential energies, and with that some of these can be proved. So if you are more interested, you can check out this chapter 8 of this book. It will also contain answers to some of these big questions and potentially more interesting stuff. Okay, so that's the end of it. Hopefully you enjoyed uh, this Braess paradox and finally understand some concepts of game theory. Thank you.